So we have a last minute schedule change. And so next talk will be Xin Zhou, who Antoine's talk will possibly switch with Xin's talk on Wednesday, and we will make an announcement on Wednesday. So we are very happy to have Xin Zhou, and who cannot be here in person, unfortunately. I think he still enjoy Connecticut. And he will talk about.
Sorry, I haven't read my title down yet.
Yeah, he will talk about the min-max minima hypersurfaces with higher multiplicity.
Oh, okay. Thanks very much for the kind invitation from the organizers for this very nice event. Due to some reasons, I apologize that I couldn't be in person, even though I really wish I could. So today I'm going to present a recent joint work with Zhichao Wang at UBC about some new examples where the min-max construction must give us minimal hypersurfaces with higher multiplicities. So today I will focus on a work that we have already finished. So where we do know that multiplicity is 2. And if time is permitted, I may talk a little bit about the ongoing work that we believe we can do this for higher multiplicities. So let me first quickly review some key ingredients behind the theory, mainly I call the volume spectrum and the min-max theory. So in short, the min-max theory, in our point of view, can be thought of as a Moore theory for the area functional defined on hypercycles. So the ingredients will be, we have a total space of hypersurfaces. So the area functional is naturally defined. So it defines critical values as the so-called volume spectrum. And we try to search for the critical points associated with these critical values. So the total space I'd like to start with is the set of Cauchy-Pauli sets or sets with finite parameters. So these are our subset of M. So M is ambient space, which I have dimension n+1 and marked with dimension n+1, such that the boundary has finite n-dimensional measure. So this means the n-dimensional Hausdorff measure of the boundary. We consider the size omega with finite boundary measure. Okay, so it's not too hard to show that this is actually contractible. So this is a contractible site. So in principle, contractible site, we wouldn't expect to always find the critical points unless trivial ones. But we do have a Z2 action. Let's say Z2, this is Z mod 2Z. And there's a Z2 action on the site, so that every set goes to its complement. Okay. We know that if we only focus on the area of the n-dimensional measure of the boundary, so this Z2 action does not change, or this HN measure is Z2 invariant. So we can consider the quotient space. So the quotient space we will denote it by Zn n+1. There's a remaining metric with Z2 coefficients. It's defined to be the set of sets with finite parameters modulo this Z2 action. Okay. So this is a contractible site. Modulo Z2 action, we expect that to have some fruitful topological structure. Actually, this was proved by Almgren. It's proved by Almgren 61 that this is very homotopic to the infinite dimensional real projective space. So now we would have many topological structures, right? In particular, under this weakly homotopic equivalence, we know that the cohomological ring of this big space under Z2 coefficients is exactly the polynomial ring over Z2 of a single generator. So where this lambda bar belongs to each one of this huge space. Okay, that is a basic topological structure. With this topological structure, in particular, we can always imagine that this total space. Sorry, this is infinity. Forgot. We can always treat this total space as RP infinity. So we expect that there are many critical points as like Morse function on RP infinity should have many critical points. To define the critical values, we have to define the so-called K-sweepers for integer K. So we say that a continuous map from a K-dimensional space into the space of multi-cycles is a K-sweeper if say that here we have this topological structure, we can do a pullback. We pull back lambda bar to the power of a case. So this will be element in the case cohomological group on the parameter space. Sorry, I shouldn't say this. I mean, this parameter space, ideally it will be a k-dimensional space, but in practice it can have higher dimensions. So let me just don't put k over here. So we require that the pullback of this cohomology in this cohomology group is non-trivial. It's not zero. Let's look for this identity. So this identity merely tells us that this cohomological group is non-trivial. So in particular, so I have to at least have a k-dimensional strata. Otherwise, this is trivial. Okay. With the definition of k-sweeper, this is something we can imagine as intuitively. Let's imagine a k-sweeper is RPK copy inside this RP infinite. Okay, that's an intuitive explanation of a k-sweeper. With the definition of k-sweeper, we can define the case volume spectrum. I should mention the names. Like this notion was first introduced by Gromov in the 80s, and then later on revisited by like Goose, I think in 2011, and then Marques-Neves in 2013. So for the current definition. So the case volume spectrum is defined as a number. It's defined so that we first pick an arbitrary k-sweeper is kind of like a k-parameter or even higher parameter family of hypersurfaces so that it detects this topological structure. Okay. We pick such a k-sweeper, then we take the maximum of the area in the parameter space. So now I didn't know this is the area. So it depends on how we treat this element. If you think phi of x at the Cauchy site modulo this Z2 action, we should have a boundary. Or if you just think about this phi of x as a Cauchy site with boundary, with an unoriented boundary, so we can just give this absolute value. It depends on what we think of. Okay. And then we take the infimum over all k-sweepers. That's the definition. This is a min-max definition. So later on, during course of the proof, I'm going to introduce a particular 1 and 2 sweepers. So I hope there I can give you a more intuitive idea of what is an example of a k-sweeper when k could be 1 or 2. So this is the definition of case volume spectrum. From the definition, from this cohomological condition, it's easy to see that this sequence forms a monotone non-decreasing sequence. So it's less equal than omega 2, less equal than omega k. Okay. So in particular, by the Lukumovich Marques-Neves well law, we know that this has a universal asymptotics in the rate of 1 k to the power 1 n plus 1 is ambient dimension. So there is a growth rate. So this growth rate has already been observed by Gromov, and it plays a central role in part of the solution of the Yau's conjecture by Marques-Neves. And moreover, Almgren also proved that the first number is strictly positive. This is the Lukovic Marques-Neves well law. So now we define a sequence of numbers. Let's say, given a Riemann manifold, I always assume this is a closed Riemann manifold. Given such a closed Riemann manifold, naturally we define a sequence of numbers. This is a monotone non-decreasing sequence of numbers with certain growth. Okay? So now we expect to show that each of them corresponding to critical values of the area function. So this means the area function. That is the min-max theorem. The theorem I stated combine a lot of efforts. I would mention the early work of Almgren and Pitts. So I then Xin Simon. So this bulk of work was done before 1981, and then recently by Marques-Neves for some further advancement on the Morse index. In particular, combine all of them, I want to state the following result. So if we consider a closed Riemann manifold of dimension between 3 and 7, for each of integer k, this case volume spectrum is realized as the area of closed minimal hypersurfaces. It's realized as the sum of the area of closed minimal hypersurfaces. So I give the hypersurface upper index to denote that it's associated with the case volume spectrum, and the lower index to denote that we may have several disjoint connect components, equals 1 to L of k, which to say that for each k, we see smooth closed embedded minimal hypersurfaces. A disjoint collection of them. So so if we can state the min-max theorem in this form, that would be great. But unfortunately, there exists a linear combinations, integer value linear combinations. That's to say, the min-max value indeed is not only the area of some disjoint minimal hypersurfaces, but each of them is counted with an integer multiplicity. So each of them belongs to positive integers greater than 0. Okay? And we usually call them multiplicities. This issue is very common if we invoke the geometric vector theory, in particular in the codimension 1 case, because, well, we can have a bunch of different sheets of surfaces collapsing together, forming this minimal hypersurface. So this is the major part of the min-max theorem, which tells us that each of the value is realized as the integer linear combination of some closed embedded minimal hypersurfaces. And Marques-Neves also proved that if you look for the Morse index, of the components, and sum I goes 1 to Lk, this is less equal than k. To be short, each of them is defined using a min-max construction. Intuitively, we can imagine that like this Euro saddle point structure. So this k parameter appears as possible ways to decrease the area of the critical points, and the remaining directions, and are those directions you can only increase the area if you perturb them. So that's a conjecture Morse index upper bound. But in general, in this theorem, we actually couldn't recover the multiplicity in this index bound in general. Okay, so I will tell you a more precise form soon. So this is a min-max theorem. well, we always know that one of the application for them is the Yale's conjecture, eventually solved by Marques-Neves and Antoine Song, where actual headache is how to deal with these integers, because for instance, well, the conjecture picture, I mean, it's not conjecture picture. The possibilities that, for instance, omega 1 equals to be sigma 1, for instance, and omega 2, if you're unlikely, it can be 2 times sigma 1, and in some very bad case, omega k can be k times sigma 1. Well, that would be the worst case. Okay, so if this was the case, we were not able to produce infinite many solutions by repeating this procedure. Okay. So today I want to explain like 2 stories. At the beginning, I will show you that if we assume some genericity condition on the Riemann metric, so we wouldn't see these bad scenarios. And the second, and the main part of the talk, I will show an example where like this phenomena does happen. We expect to show that by extending our current technique, we can able to show that in a particular metric, this would happen. Okay. So now let me quickly review some histories about how people deal with the possible existence of multiplicities. There were actually quite a lot of results, but let me just review a few that's related to our talk. So in the beginning, around nearly 10 years ago, people still only stuck with a case for 1 parameter family. So K denotes the number of parameters. So for the 1 parameter in my constructions, so if we assume an additional assumption that the Ricci curvature of ambient space is positive, by combining the work of say Marques-Neves in 2011, by combining my thesis in 2013, and then combining a later work by Marques-Neves, Catover, Marques-Neves in 2015, they actually show that we always know there's only 1 connect component, and this guy is 2-sided, or I mean, let's assume that the ambient space is orientable. This is to say that sigma 1 is orientable, it's 2-sided, and the multiplicity is equal to B1. So that's the first set of complete work. Well, this is then a conjecture picture by Marques-Neves that for generic metric, this should always be the case. So this was later confirmed. So for 3 manifolds, this was later confirmed for generic metric by Chodos Mantolidis. So in 2018, so they show that so for all k, if G is a generic metric, each of the component is 2-sided, and multiplicity equal to B1. Okay. So they use this Allen-Kahn approximation for the area functional. You have to regularize the area functional and show that under the appropriate regularizations, when you take the epsilon go to 0, you show that if this condition is not satisfied, then you contradict the generic assumption. Later on, for all dimensions, and G is generic, this was the same condition was solved by myself, 2019. Again, I just proved that. So this condition is true. Okay. So this work sort of you recall the multiplicity 1 conjecture. Formulated by Marques-Neves. Okay, so I want to just state a corollary of this multiplicity 1 conjecture. So let's see that under the multiplicity 1 conjecture, we know that the integer is equal to B1. So this is very nice. So then you can imagine, given arbitrary metric, you can approximate the arbitrary metric by those generic metrics, and then study how the solutions converges. That will tell us something as follows. For general metric, say we call non-bumpy, So bumpy sort of is a generic assumption. It's a generic notion. So what we can show is that if a kinetic component is either one-sided, or if corresponding integer multiplicity is greater than 1, under either of the assumptions, we can show that this component is called weakly stable. I mean, another way of saying that is if you look for the Jacobi operator corresponding to the second variation of the area functional, the first eigenvalue equal to be 0. That means that it's stable, but it carries a non-trivial Jacobi field. And actually, by elliptic theory, we know that this Jacobi field have to be positive or has to be the same sign. So now let's quickly review the picture. We know that generically, if the metric is bumpy, the min-max theory does give us a distinct list of minimal hypersurfaces, and by the later work of Marques-Neves, this can be a equality instead of just less equal sign. That was a very satisfying bulk of results. Tells us that the area functional obeys just like a Morse theoretical properties. So generically, it's a Morse function. It carries all critical points of the associated index. Okay, and the corollary tells us that if the multiplicity one result does not hold true, then the possibility is that it's weakly stable. So this then leaves a general question. The question is whether the cases can actually happen, whether the multiplicity can be greater than 1, or whether a component can be one-sided. Today I will focus on the multiplicity part, as sort of one can show the second by the first in our work. Let me first show you a trivial example, where in this trivial example you can see. Let me show you the picture. A trivial example is that the ambient space is like n-dimensional sphere radius 1 crossed with circle radius a, where a is very large. So that's a sort of a thin and long torus. So in this case, it's not too hard to see that the first width, equals to be the area of twice of the cross section, cross any parameter t. So the area, the min-max equals 2 times such cross section. But since this is a product metric, we can use our hand to split off this multiplicity 2 surfaces and write it as say T1 plus cross T2. Okay, that's to say I can pick any 2 copies as far as they're disjoint. They still form the min-max minimal surfaces. Now here I want to explain that in the min-max theory, the statement tells us that there exists a set of minimal hypersurfaces whose area sum up to be this number. And we actually have no way to show which surfaces is exactly the min-max surface corresponding to the number. So in this picture, as far as you can find 2 of them, then you can always find a multiplicity 1 solution. So question is, by this trivial example, do we actually see them? Or say, if you see a multiplicity 2 min-max minimal surfaces, can we use our hand to split them off to make them generically make them to be multiplicity 1? So the recent results I want to present is that the answer is no. We do find the following example. So this is a joint work with Zhichao Wang at UBC, and the paper is posted early this year. We consider actually a sphere, ellipsoid embedded in Rn plus 2. Well, let's assume that we are in the smooth dimension range. The sphere we consider can be written out explicitly. So it's A to n equal to B1. So where A is very large. So the picture is that we consider such an ellipsoid. So this cross section, we call it as N0. So it's just as intersect with Sn plus 2 equal to B0. And this height is A greater than 1. Okay. We consider this particular ellipsoid. So before I state, let me state the result first. Then we show that the second min-max width, this surface is equal to be 2 times the area of Sn0. Or I should say that this is the only minimal surfaces that realize this area. Okay, so when I state this, I show that the second min-max equal to be 2 times area of this cross section, and moreover, we prove that this is the only minimal surface that realize this number, whose area realizes this number. In course of the proof, I will also show you that the first width this is not hard to see, equal to be the area of the cross section. So the first width equals that. I will write out a sweep out with you. Actually, the one sweep out is easy. These are just those parallel spheres. So this gives a one parameter family of hypersurfaces whose maximal area is this one, and you can show that this is the optimal one parameter family. So then we are going to show this. That's the major part. Any questions or comments up to now? Okay, so I like to just use some time to explain the idea behind. So the idea behind is involves a lot of I think interesting ideas of minimal surfaces in this type of manifold. Okay. Before I go on, let me just give some quick comment over here. So we can check that if you calculate the Ricci curvature of the metric, is strictly positive, except that the Ricci curvature has a null direction along this cross section. The Ricci curvature in this direction is 0. Okay. So therefore, if you're familiar with the Frankel theorem, you know that if you have two minimal surfaces, they have to intersect with each other because you cannot have two minimal surfaces. I mean, given any two minimal surfaces, one of them have to go into the region where Ricci curvature is strictly positive. I mean, in other words to say, you have a minimal hypersurfaces. If you're not this cross section, then you have a point Ricci curvature is strictly positive. So the classical Frankel theorem tells you that have to intersect. So okay, so that's the main result. So next I want to explain the picture for minimal surfaces within this long ellipsoid. So to explain that, I mean, I first would like to introduce what are the one sweep out and two sweep outs in this picture. Okay, I made a definition which is very abstract, but now I make it more intuitive or more direct here. So a general way to produce one or k sweep out is to consider a Morse function. So that this part is general for any closed n+1 manifold. Okay, let's consider a Morse function. The one sweep out I denoted by phi1. Well, we can construct something defined on RP1. Well, RP1 is S1, but I write it this way so that we can use homogeneous coordinates. So from RP1 to Vn and n+1, V2. General way is to say that given a homogeneous coordinate AB, what we do is to consider this function AFX plus B. This is another Morse function. We look at the superset and look at the boundary, and then quotient this Z2 action. Now, in this particular picture, the function f I'm going to pick is nothing but xn plus 2. Well, it's easy to check that fn plus 2. Yeah, it's easy to check. This is a Morse function on this ellipsoid. Well, you can only have 2 critical points, and either of them is non-degenerate. Okay, so the level set are parallel circles. So if you're plugging in this definition into here, which means that given a homogeneous coordinate AB, we just identify a particular cross section in this direction, a level set. Okay. So this one parameter family, the one-state plot is just this one parameter family of level sets of xn plus 2. So then how do we produce phi2? We can produce that using a similar way. So this time the homogeneous coordinates contains 3 numbers, A, B, C. So this will be mapped to what we do is we take A f square plus B fx plus C. This is another, I wish this is a Morse function. Okay, yeah, I think we can check that. So we look at the supersite again and take the boundary and take the Z2 quotient. Well, if you look for what site, I mean, this will be exactly the 0 sites for almost all ABC, there will be the 0 site of this polynomial, right? And if you're going to solve this, we will get at most 2 copies of the cross sections. In particular, in this case, a slice in phi2, will be like 2 cross sections of this long ellipsoid. Okay. So in other words, if I write it in words, I would say that what phi2 did is phi2 picks up 2 slices of phi1. Okay. So this is the 1 sweep out and 2 sweep out. In particular, what we want to show is that this is pretty easy. We want to show that if you look for the 1 parameter family given by the level set of this function, this is the optimal 1 parameter family. Namely, this area is the minimum among the maximums of all such 1 parameter families. So it's mainly hard to show that this gives the optimal family for the second volume spectrum. So let's just go on to see a little bit more. First, I say it's a lemma. The proof is there are many ways you can prove that. I want to say that omega 1 of this particular manifold equals the area of Sn 0. It's a cross section of the level set corresponding to 0. Okay. A basic corollary of this lemma is that omega 2 of this manifold, I mean this is equal to the infimum of the maximum. So of something will be less equal to the maximum of the area of phi2. Okay. And I try to emphasize that each slide of P2 consists of 2 slides of phi1. And the maximal area slide of phi1 is this number. So this will be equal to be 2 times Sn 0. Is that okay? So we construct a particular 2 parameter family so that its maximal area will be 2 times this cross section. So that's the upper bound. So now I'm going to show that there does not exist any other minimal surfaces whose area is less than this, unless this guy for A large enough. So before I continue, I like to quote a so-called catenoid estimates first by Katover, Marques-Neves, and then by Haushofer and Katover. first by Ketterer, Marques-Neves, which I mentioned before, and then by Haushofer, hopefully, yeah, Ketterer, I think 2018. So particularly I want to emphasize the work by Haushofer and Ketterer. They consider, they want to show that under non-degeneracy condition, the second min max is realized by minimal surfaces, which is not twice of this guy. So let me write down what they did. I mean, they can deal with a large class of manifold, but let me just pick a particular example to illustrate what's the idea. The example that the work of Haushofer Ketterer can deal with will be something like this non-degenerate long ellipsoid. So note that the difference is, so in my example with Zhichao, we have to raise this to 2n. And in their example, they consider exactly the case when the Ricci curvature is strictly positive along the cross section. So what they consider is something as follows. So if this is the SN0 in their picture, so what they consider is to consider two slices close by and open a neck, adding a catenoidal neck, open a disc and add a catenoidal neck. So let me call this part as an epsilon as n minus epsilon, and call this disc 1, disc 2, and call this part the catenoid. So the key idea of the catenoid estimates tells us that if we calculate the volume, the n-dimensional area minus area D1, D2, add the area of the catenoid, this will be strictly less than 2 times the area of a cross section. Geometrically, if this cross section is non-degenerate, I mean, if the remaining, yeah, if the Ricci curvature is strictly positive, or if the second variation of the area function along this cross section is non-degenerate, then you can remove 2 disks and then adding an catenoid to reduce the area. Okay. Well, for us, for the work of joint work with Zhichao, what we show is that on our SNA degenerate surface, the converse holds. The converse holds. How to understand that I claim the converse holds? If you have a surface which look like that, it's easy to show that if the cross section is degenerate, the area of this will be strictly greater than 2 times of that. We actually have to show more. We have to show that if you have a minimal surface which is close to 2 copies of this cross section, is the surface itself is a mimic of something like that, and then you can calculate the area. Okay. So in the last 10 minutes, let me just quickly go through the outline of a proof of our work. So where I'm going to show you what I mean by saying that the converse of the catenoidal estimates must hold true. Okay. So we prove by contradiction. So suppose that the second width on this long degenerate ellipsoid equals multiplicity 1 minimal hypersurface. So this guy has multiplicity equal to B1. If I plot a picture, well, by if I plot a picture, sorry, this is not very good. If I plot a picture, what I mean is that I have another minimal surface, which sort of should mimic a double copy of the core. Well, here we have to first spend some efforts to show the following. We have to show that when a goes to infinity, we have to show that this sigma a converges to 2 copies of Sn0. Is that okay? So well, I think this part is interesting, but maybe I don't have enough time to explain all the details. The idea is that when a go to infinity, if you look at the say the smooth limit or Cheever-Gromov limit, the limit of the manifold will be a cylinder. Will be the limit will be Sn0 cross R. So there you have the you have the minimal foliations. The minimal foliation argument tells you that the limit can only be an integer multiplicity of this guy. And moreover, we know that this surface has Morse index bounded by 2 and the area has upper bound, then there are good compactness theorem, which tells us that this convergence is actually smooth away from 2 points. At most 2 points. Okay. So now we have a theorem A. The theorem A says that assuming you have a multiplicity of 1 minimal surfaces which converge to 2 copies of the cross-section away from 2 points in this configuration, we show that the area of sigma A is really greater than 2 times Sn0 for A large enough. So so first, this forms a converse to the catenoidal estimates, because by catenoidal estimates, it tells you that you can construct comparison surface with area strictly less than 2 times our cross-section. And our result says that if you prove by contradiction, those sequence of minimal surfaces eventually will have area greater than that. So this is the converse. On the other hand, the theorem already tells us that this cannot be true, because we already showed that omega-2 is strictly less than 2 times of that. So therefore, everything reduces to this theorem A. This is area comparison result. So from now on, everything below will be purely like compactness analysis for minimal surfaces. So let me just show a major picture or the major steps to deriving this area comparison estimates. First, I say that this convergence is smooth away from 2 points. This follows from an index upper bound and area upper bound together with a minimal foliation argument at the limit. So let's assume for simplicity that only one singular point, or let me see, the singular point is P belonging to Sn0 belonging containing Sn plus 1A. Okay, I have a point P. Okay, the convergence is smooth away from the point. That's the picture. So now if we do a blow-up analysis, we can actually show that sigma A minus P denote divided by some sequence of numbers, it has to convert to a standard catenoid. So there are several ways to recognize this. For instance, so Rick Shin has proved that if you have a complete minimal surface with 2 regular ends, it has to be the catenoid. Well, for us, this surface has uniformly bounded Morse index, has a uniformly bounded area ratio. You can apply that. So that's to say at this part, it's more or less a scale down of a catenoid. Well, we can write down what is a catenoid at this moment. The catenoid, I mean, the original catenoid is nothing but how to say that R equals quotient of V. This is the a polar coordinate, cylindrical coordinates. In the cylindrical coordinates, the catenoid is written by this formula. Okay. So that tells us the height function is roughly log of R, right? So the original picture will be a scale down of the standard catenoid by a factor I called it RA. Let me write this as RA times catenoid. That's to say I have to scale, originally the radius is 1. I have to do a rescaling so that this is RA. So in that case, the height function is written as RA times log R over RA. Okay, so that's the height function. So using the height function, so we can estimate what's the area of this catenoid inside. Let me use a different color, sorry. So we can estimate the area of the catenoid. So the area of the catenoid in a large enough ball equals more or less 2 times 2 pi r, sorry, 2 times pi r square. I mean, r is this radius, plus a large constant. A large constant can be a c times log r minus 1 times, sorry, I have to multiply this with RA. Yeah, is that okay? So I pick large radius r and calculate the area of the catenoid. That's the leading term is area of the disk, and the remaining term is a high order term, but it's a large constant times RA square. RA is the radius of the scale down of catenoid. Okay, so that's the area of the catenoid. Then we prove a key theorem, which maybe I don't have time to really go to the proof. We show that if you consider the regional surface dig out of this ball, I should call it A anyway. So it's written as a 2 connect component, A1 union with disjoint union with sigma A2, and the Hausdorff distance between either of the connect component with the core is bounded by C times RA times log of RA. In other words, so here we actually know that the height function here is RA times is less equal than RA times log of RA. So what we try to prove here is that if you look at the large scale, so this is a small scale where we zoom in. If you look at the large scale, what we see is that we have like 2 sheaths, another 2 sheaths. So the inner scale is small RA, and then we pick a small ball whose radius is capital RA, and then we claim that even outside this ball, the height function is more or less controlled by RA times log of RA. So where this is exactly the scaling down of the critical catenoid, the height of scale down of critical catenoid. Okay, so assuming that we have this height estimates, let's see how we can combine the remaining part of the proof. So what we consider is that so inside the ball, we do know the area is size of this, and outside this, we use a height estimate as to get an idea of the area. So what we consider is for instance, say sigma A1 outside this ball of RA. Now what we do is we added D1. So where D1 is this disk. So this we call D1. So this is sigma A1. We consider this area. So actually, so in the ambient space is this ellipsoid. The ellipsoid has a mean convex foliation. So there's an area calibration arguments tells us that if the height is at this order, the area will be greater or equal than the core. Well, I'm thinking like dimension 3. So let me assume n equal to b2 for simplicity. So the area is less equal than the height to the power of third. So I'm assuming n equal to b2. So this is a case where we use this degeneracy condition. So if this minimal surface, if this core minimal surface is non-degenerate, when you push forward, you get area upper bounds by this to power of 2. But the core surface is degenerate. When you push away, you can get area lower bound by a third power arrow. So now I think I can finish the proof. So let's see what we already obtained. We have obtained that inside the ball radius RA, we have area estimates. Outside the ball of RA, we have this area lower estimates. Now we add them together. We add the star 1 with star 2. Well, we have 2 copies of star 2. So what I'm doing is star 1 plus 2 copies of star 2 by moving this to the right hand side. So let's see what I obtained is that the area of sigma A equals the cotinoidal parts BRA plus sigma A1 minus BRA, plus sigma A2 minus BRA. Okay, so I them together. So this is greater or equal than 2 times pi RA square plus a large constant times small RA square. So minus two disks. I chose this so that these two are almost the same. Let me just abuse the notation a little bit. Minus 2 times pi RA square minus C times RA log RA to the third power. So in particular, we have to show that these are small order, so this cancels out. So this is to be bounded out by C1 times RA square minus C2 times RA cube log RA cube. So the main point is to notice that RA times log RA to any power. Well, what I'm going to do is I rewrite this as RA square times RA. I want to show that this term, which is this term, converted to 0 as RA convert to 0. So that's it. Oh yeah, I forgot 2 copies of this guy. So plus 2 copies of this guy. So we'll have a strictly sign of what I want to prove. Okay, so let me quickly summarize. This part is a bit technical. What we want to show is that suppose the min-max minimal surfaces is multiplicity 1, then it have to be something which like multiplicity 2 copy desingularized by 1 or 2 necks. And then we compare the area of the necks and the area of this remainder part. The area of neck is estimated by direct computation and smooth convergence. And the area of the remainder part depends on the height estimates. We want to show that it couldn't go up too much. So combining all, we have this area estimates. Okay, I think I should stop here. Thank you very much.